Our next speaker, while they're bringing it up, is Hillary Egan from the University of Colorado. Her talk is on astrophysics, and her advisor was David Brain at the National Renewable Energy Laboratory, was where she did her practicum.
All right. So those of you who knew me from the beginning of this fellowship know that this is nothing to do with what I applied saying I was going to do. I used to work on computational or cosmological simulations of galaxy clusters. So this is about as far apart from that as you can be and still be in an astronomy department. So I think that's a real credit to Krell and the CSGF fellowship for allowing me to pursue the science that I found interesting with great people and not be constrained based on who may or may not have funding at the particular point in time. So this is a really exciting time in exoplanet science. There are a lot of really great telescopes discovering new planets every day, like Kepler and TESS, which was just launched a couple weeks ago. And we've discovered so many interesting types of worlds that we had no idea based on looking at our own solar system. Things like mini Neptunes, super Earths, planets in binary systems, lava worlds, ocean worlds. I think it's a credit to how exciting this is that you cannot really distinguish actual NASA press release pictures from screenshots from Star Wars where there are no droids. So one of the coolest areas right now is thinking about potentially habitable planets. And so there's a big question of how do you define habitability? The classical definition of this is a habitable planet is one that's capable of supporting liquid water on the surface of the planet. This means that the temperature of the planet at the surface has to be below boiling but above freezing. And you have to have an atmosphere in order to prevent immediate evaporation of that water. And this is really a definition that ignores a lot of things like surface irradiation and also ignores other less observable forms of life. Planets or moons like Europa have subsurface oceans, which are definitely capable of supporting some sort of life. We pretty much have no chance of observing it using current telescope capabilities. So that's why we consider mostly this definition. And so in order to be in this proper temperature range, that's going to really depend on the environment that a given star is producing for a planet. So for a hotter star, you have to be further away in order to be in this habitable, appropriate temperature zone. But for a cooler star, you need to be a lot closer in. There's another important component to this. In order to have this atmosphere, which is preventing all your water from immediately evaporating away, you need to maintain your atmosphere over long time scales. And this is not a given. Just because a planet forms with an atmosphere doesn't mean it's going to have one over the entire course of its lifetime. There's evidence in our own solar system of long-term atmospheric evolution on planets like Mars, which used to be capable of supporting liquid surface water. It has all sorts of cool river deltas and geologic features saying this, but currently has pretty much no atmosphere compared to something like Earth or Venus. So this escape of this atmosphere, pretty much the atmosphere can either go into the rocks in a process called sequestration, or it can escape to space. It has to go somewhere if it's not on the planet anymore. And so I look at the process of how these atmospheres escape to space. This can happen in the form of neutrals or ions. And I think ions are particularly important and interesting because of the additional energy sources that are able to accelerate these ions in the form of electric fields out from the planet. And this becomes really important for heavier species that make up an Earth-like atmosphere, like oxygen, carbon dioxide, nitrogen, etc., where hydrogen can easily escape via neutral escape. And even within ion escape, there are different channels that this escape proceeds through based on the different acceleration mechanisms and different local areas where this acceleration is happening. Okay, so in order to really understand all these different channels and how the ion escape proceeds, this is where we start to need to use simulations. Essentially, these are set up using a sort of box where from one side of the box you set a solar wind, so wind emanating from a star will start to erode and be an energy input into our atmosphere. And then we have a lower boundary on the surface of our planet which is set by the planetary ionosphere. And so this is the ionized portion of the atmosphere that's at the top. And then the size of our box, the area that we have to simulate, is dictated by the size of the planetary magnetosphere and this interaction between the solar wind and the planet. There are a couple usual model choices in how you approach these in the physical equations. First is just a typical magnetohydrodynamic model, MHD, where ions and electrons are both treated as fluids. And then there's a hybrid method where you treat the ions as macroparticles, and then the electrons are sort of a background charge neutralizing fluid. And using the latter method, a hybrid method, will really allow you to get at sort of the ion kinetic effects that can be important in these interactions. One great reason to approach this problem from a planetary science perspective, rather than just coming at it from our telescope's astro interpretation, is that we can actually validate these models using in situ spacecraft measurements. And so this is a figure from a paper I wrote up this past year, where we compared 5 different models of planetary magnetosphere, 3 MHD, 2 hybrid models, to actual data gathered from the MAVEN spacecraft, which is currently orbiting Mars. And so this process, we've got our spacecraft, it's orbiting Mars. We measure the solar wind directly, so outside of the interaction region with Mars. And then we also take data along this orbit in other interesting areas closer to the planet and behind the planet. Then we simulate the same region using the same upstream input conditions for all of these different models, and then compare across the models and to the data itself. So here I'm showing, doesn't matter. Here I'm showing on the top panel the H+ number density, and in the bottom panel magnetic field magnitude over time in the orbit, where the white is showing actual data from MAVEN, and all the different colored lines are the model results. And you can see that, especially in the top panel, there's this sharp drop-off in H+ number density that the hybrid models are reproducing well, but the MHD models have this smooth transition because for this set of solar winds, the MHD models are much overestimating the extent of the bow shock. And so that's a key difference here that says, okay, if you're looking at this phenomenon, it's really important to use a hybrid model. But there are other regions from this whole paper, there are so many different places that we needed to compare that the MHD models do better from the hybrid. So it's important to choose your tool appropriately in order to reproduce the physical phenomena you're interested in. So for the rest of this talk, I'm going to be discussing results used I've gotten from the R hybrid code, which is one of these hybrid models. And this is sort of a shout out to, this is a high performance computing scenario. Some of the important features of the problem is that it's a really coupled problem across a huge variety of scale sizes. A typical ionosphere scale height is on the order of tens of kilometers, where your magnetosphere size is on the order of thousands to tens of thousands. And the problem gets even more complicated when you introduce an intrinsic magnetic field. Also in hybrid methods, we're not just constrained by our grid. We have hundreds of particles per grid cell that are representing these ions, and they're not constrained based on where you inject them. So we use some dynamic load balancing and good propagation schemes. I'm also showing efficiency testings I ran on CU Summit, which is a supercomputer that CU has helpfully decided to call Summit because that's not at all confusing for anyone. Okay, so how do we apply these solar system plasma models to exoplanets in a useful way? This is essentially a change of boundary conditions because all of the physics involved in the interactions is the same. So there are 2 portions to this, how the stellar input changes, so what kind of wind we're setting at one side of the box, and then how the planetary properties themselves change. So we've got to think about what should these new inputs be, and is the model still valid? And this is a point that I harp on a lot more when I'm giving science talks to people in my own field, because I think there is a tendency to trust models blindly, and whatever it says must be right. And this is something that I think that we, as a computation community, do a good job, but can continue to make a point to introduce even more of when is our model valid and how do we trust it? What are the sorts of error bars that we can put on it when comparing to real data? So the first part I'm going to talk about is scaling the stellar wind input conditions to conditions that are appropriate for many of the planets we're finding as exoplanets. M-dwarfs are one type of star that are we find a lot of really great targets for finding habitable planets. And this is because M-dwarf stars are cooler, so the habitable zone is closer in because you have to be at that right temperature. And that means that they're easier to observe the planets using our telescopes because the star isn't quite as big and bright. They're also the most common star in the universe, so that's also very helpful. So this is cool, but the stellar environment is really challenging because it's a lot different than the solar stellar environment. There's more intense solar wind. If you think about it just based on the amount of flux that's passing through an area when you're closer to the star, it's going to be higher. They also, because they're a different type of star, emit more strongly in the extreme ultraviolet. And this is the sort of wavelength range that really drives heating of planetary atmospheres. And so that's a really important component for our models. They also tend to be more variable stars. They flare a lot, so that's important to note. And the stellar magnetic field is more radial when you're closer into the star. And I've sort of put up a diagram here of why that is. Every star has magnetic field lines that extend directly out from it. When you are close to the star, all of the plasma is pretty much co-rotating with the star itself. But as you get further and further out, these magnetic field lines bend as the star starts to rotate. So when you're in this outer blue circle, you can see that the pink lines where my magnetic field, they're more tangential to the planet's orbit, but when you're closer in, they're more radial. And because ions are confined to travel along magnetic fields, this has really big implications for how ion escape can proceed at planets. So this is something that I've just pretty much finished working on and submitted a paper right now. I've ran a bunch of different simulations, each changing one of these parameters at a time, so you can isolate the influence of each of them on the ion escape from the planet. So here on the right, I'm showing a bunch of my different fake planets as the little sphere, and the colors are showing O2 plus number density, and the white lines are magnetic field lines. So you can see as I'm turning them, I'm also increasing the EUV in one of these and increasing the stellar wind flux. So we find that both the ion loss rates and the overall morphology of the interaction change significantly when you change these different parameters. And processes that are spatially distinct in the solar system planetary ion escape are not necessarily distinct when you look at this interaction with a radial magnetic field, for instance. And so if we're trying to take these processes that we understand from observations of our own solar system and scale them to exoplanets, we have to be really careful about our definitions and not just say, oh, all the stuff that's coming off the top of the planet in this one configuration is going to scale like this, because the interaction works very differently. Okay, for the last part, I'm going to be talking about how the planetary properties can affect our notions of ion escapes and how we can use our intuition from the solar system, again, to drive this. So two of the properties that are really important in understanding the plasma interaction are the planetary radius and the intrinsic magnetic field of the planet. Again, because ions are constrained to travel along the magnetic field lines, and because the gyroradius of ions approaches the size of the planet in a lot of these cases, or is even bigger. So changing your planetary size has a really big impact on both the interaction size itself, but also the size in comparison to the ion dynamics. So we have a bunch of planets that we can plot in this kind of two-parameter space that I'm interested in right now. We've got the Earth, Venus, which is pretty much the same size as the Earth, but lacks an intrinsic magnetic field. We have Mars, which is a bunch smaller, again, lacks an intrinsic magnetic field, and Titan. And all of these planets, we have in situ observations of how ionoscape is working. So we're able to constrain this parameter space. So what I'm interested in doing right now, I was hoping to have real results for this conference, but they're still half-baked. So next time is exploring this entire parameter space with models and understanding the relationship between these properties and ionoscape. And be able to constrain what we know based on observations in our own solar system. We ideally want to use properties that we can actually observe using exoplanets in order to have some sort of guess on what planets will maintain atmospheres over long timescales, so we can have these good estimates for follow-up observations. Right now, typical exoplanet discovery techniques, we can find planetary size pretty easily, mass, but in order to find an atmosphere, you need to look at the planet for a lot longer and use a much bigger telescope. We're hoping that James Webb or JWST will eventually launch someday. It keeps getting delayed, so we'll see about that. But in order to observe planets with a telescope like that, we need to select our targets carefully. And so this will help play into how do we select those targets well, using properties we can actually observe easily. So with that, I think this is a really exciting time for exoplanet science, and I'm really excited to be able to bring high-performance computing into this. Atmospheric evolution is incredibly important for habitability, and it's not so easy just to say you have a magnetic field or you don't. There are a lot of things that go into this, and that it's important to use validated models in order to make actual predictions that we can use. And both stellar properties and planetary properties both play into ionoscape. Thanks.